Desktop audio is being recorded. Hell yeah. So, let's just hop into it. So, first thing we want to know is, what is the Biot-Savart law? Or what is the BS law?
Um,
Or what does it let us do?
results. Uh, it's a results for the infinite wire and a loop.
So what do you mean by that?
Uh, we can apply Biot Sarvit law. We can apply the results of the law for an infinite wire and a loop.
To do what?
I to figure out the current and the magnetic field.
Magnetic field. That because we're usually because essentially a magnetic field. How are magnetic fields generated?
Uh, the charge is going through the current.
Essentially, charges when you have some sort of charge moving, traveling,
Moving.
you're going to be generating some. You've seen those. I'm sure maybe you've seen at some point in like a high school physics class or whatever. You've seen those like videos of, like a particle traveling along and it like a photon and it creates the perpendicular electromagnetic fields.
Yeah. Long
Basically,
time, yes.
yeah, like you've seen that thing where it's like that's basically how magnetic fields are generated. Magnetic fields are generated by charges traveling, essentially. And a current is literally just a bunch of charges traveling along, for example, through a very long straight wire or through a wire loop. And so we can use the Biot-Savart law to find the current that is generated. So what is Ampere's law then?
Uh, well, I know Ampere's law is it's only useful in symmetric cases, similar to
Exactly.
Newton's law.
Mm-hmm. And what does it let us do?
Uh, I'm trying to remember specifically. I know it's. I know the result of it becomes U naught times the current enclosed. I'm
So
trying to remember specifically what is used for it.
So why do we use Gauss's law with electric fields? What does Gauss's law let us do?
Uh, we find the charges within a surface.
Mm-hmm. And what useful information are we able to get from that?
Uh,
Like if we have a Gauss's law problem on a quiz, what was the final quantity that he was usually asking for?
what was the electric field?
Exactly.
Okay,
We
okay. So in this case, we use Ampere's law to find the magnetic field.
exactly. But like you said, it's similar to Gauss's law. It's only useful for symmetric situations. So what sort of symmetric situations do we have?
Let's see. Cylindrical, square, circle, stuff like that.
What were the three types of symmetry we saw for Gauss's law?
Sphere, cylindrical, and forgot the third one. Plates?
Yeah, a planar symmetry where it's like an infinite
Plane.
plane.
Okay.
Are we able to use all three of those for currents with Ampere's law?
Uh, I believe so.
There's one we can't use.
Oh, cylindrical? Would cylindrical not work? Actually, no, it should.
Cylindrical is the simplest one because it's like a single wire, single
Yeah,
infinitely long wire. That's a cylindrical symmetry.
yeah, never mind. That should work. uh, and then I believe one of the examples he went over actually had, I think, did it have a sphere or something else? Huh. Which one did not work? I don't think he actually went over which ones did not work. Huh.
It's essentially you can't really do a spherical symmetry example with Ampere's law, at least in the context of this class, because the current really doesn't have anywhere to go, and for the sphere, it's going to have to like loop around in some way, and it's just, at least in the context of this class, you guys will never see any spherical examples. It's only going to be cylindrical, so like long straight wires, and planar symmetry, where you have sheets of wires.
Okay.
So, what exactly? So you mentioned something about something is equal to mu naught I enclosed. So what exactly is Ampere's law itself, like the equation?
Let me get back to that. The equation is the closed loop of the electric field dot dl, and I believe dl is supposed to be like the distance.
And I'm going to make an assumption and say that you meant to say magnetic field and not electric field.
Did I say electric field?
Yes, you
I'm
did.
sorry.
So
I meant magnetic field. My bad.
So B dot dl.
I believe that's supposed to be an L?
Yep.
Okay then.
Is equal to what?
U naught I enclose.
Yep. So what exactly is dl?
I believe it's the distance between two things. It should be.
The distance between two things, but it's a closed integral, right? So any closed integral, we integrate throughout an entire surface, so we would have to come back to our starting point.
Oh. Trying to remember what that DL means then.
There's one other example from last week, I believe, where you were doing something with an integral that involved dl. With electric potential.
Oh, so it's supposed to be the length?
It's a line integral. Essentially, we're integrating along a chosen path.
Oh, chosen path. Okay.
So, what sort of path do we take here for this magnetic field? So, for example, if we have a cylindrical symmetry situation, if this is our wire's cross-section, say it's going into the page, what sort of integration path would we take?
We take the path along the magnetic field?
Exactly.
I think?
Exactly.
Okay.
And what does that look like?
Well, by using the right-hand rule, I guess.
So what does our magnetic field look like?
Into the page. So it should be going clockwise?
Yep, clockwise, and just looping around our wire. So our path integral would be along the magnetic field. So essentially it'd be a circle. You know, like we could draw like a Amperian surface. It'd be a circle that we integrate over, or we integrate around the circle, and we're able to use that to calculate the magnetic field.
Okay.
You have any questions?
No, that makes sense.
Yeah. It's not too difficult, and honestly, you'll see it's very similar to Gauss's law, and it becomes very easy.
Yeah, I wasn't during the discussion. That wasn't really the Ampere's law wasn't that much of an issue at times.
Yeah, because realistically, magnetic fields and understanding the concepts are, I mean, are a lot of what you're expected to understand for this part of the class. And he isn't going to throw super duper complicated, annoying problems at you for Ampere's law. Like, and as long if you were comfortable with Gauss's law earlier in the semester, you'll be 100% set in Ampere's law. If you weren't completely comfortable with Gauss's law, you'll probably still be fine.
Yeah, I think I got to a comfortable point with Gauss's law, so I think this should be okay.
This will be a breeze then. So let's go ahead and hop into an example. So we're going to go ahead and have an infinite wire carrying a current I naught is equal to 3 amps to the right. And we're going to place it along the x-axis. Essentially, infinite wire right there, current to the right, 3 amps. And we're going to go ahead and place a second infinite wire 1 meter above it. So first thing I want to know is, what is going to be the magnetic field a distance r away from I naught? And what direction is that going to be in?
So let's see. So we place another wire on top, at the top.
Above it, yeah. But for now, we're going to ignore the wire, the second wire. We just want to find the magnetic field based on the first wire.
Oh, okay. So let's see. The current is going to the right. So the magnetic field should be, well, it should be going in, like at first inward and then back outward. If I had to at least say if the right was going into the page, it would be going clockwise.
The right. Okay, so if we're below the wire, what direction is the magnetic field going to be in?
Low. So, man, what's the proper word for this one? It's like I understand what the question is. It's trying to say how it rotates is the problem.
Well, you know the magnetic field is always going to be perpendicular to the current, right?
Yes.
The current's going to the right, so you have essentially 4 options for the direction. It's either up, down, into the page, or out of the page. Or like anything in between that, but it's going to be one of those 4.
I think the proper way of saying it is down. Wait a second. Actually, no. You said to look underneath it, right?
Yes, underneath the wire.
Okay, so I'm looking down here. So if I'm down there looking at it, the current should be up, I think.
So the current is going to, you mean the magnetic field is going to be up?
If we're looking downward, I believe so.
When we're below it, so the magnetic field is going to go up and point into the wire?
I think so. Because it's going to the right. Let's see, what's our right-hand rule again? Because I believe magnetic field for the wire, point thumb in the direction of the current. Wrap fingers either clockwise or counterclockwise. So in this case, it would be clockwise. It's just, if I look at, that's what I mean, like trying to say which direction is while looking on the right way is tricky. I said, if I'm looking straight at it, it should become, the magnetic field straight at it should be coming straight towards me at that point. And then if I look underneath it, it should be going, is it up?
You're off by 90 degrees here. If you're looking, so rotate your fingers. So you're curling your fingers, and you see how they like your thumb's pointed off to the right. It's sort of like an awkward position, and you feel like you're like sort of breaking your wrist.
Yeah.
But so you see your fingers curl up, and when your fingers are above your thumb, they're curling towards you, and below your thumb, they're curling away from you.
Oh, so okay. When I look it straight at it, then it should be going down.
Exactly. So
Okay. That means if I look underneath it, if I just do a 90-degree turn on that one, it should be definitely be pointing away from me. So,
yep, into the page below it.
okay, into the page below it. And then that means it should be the opposite in the other way on the top. So, out of the page.
Yep, exactly.
Okay. Whew. Visualizing like that. Okay, now that one I'm going to have to get a little practice in.
I definitely see you're more comfortable when we have currents going into or out of the page.
Yeah, I got used to that quickly.
Yeah, I mean, because it's simple. You just stick your thumb and you...
you stick your thumb either into, like, literally if you had a piece of paper, you if it's into the page, stick your thumb on the paper. If it's out of the page...
Just stab your thumb through the piece of paper.
Basically.
Hand your quiz back, and Dr. G would be like, "The hell? Why is there a hole in the quiz?"
Sorry, out of the page.
Yeah. So then, if we have our second wire up here, and if the current is traveling parallel, so in the same direction, what direction would the force on the upper wire be?
The force. Same direction. So the top wire, the upper wire, the force should be going down.
Mm-hmm.
And then the bottom wire, the force should be going up.
Exactly. Parallel attracts. But I'm guessing you are saying that because you've just memorized that parallels attract, anti-parallel repels, right? How could we use the right-hand rule to find that?
Right hand rule to find that. It would be. Would we use that second rule? The force. Yeah, we would use the force. It's equal to the current times the length of the wire across the magnetic field.
So, what direction do your fingers point?
Point fingers to the current, so it will go right.
Mm-hmm.
Put rotate palm that faces the direction of the field. So I'm guessing the field would be out of the page.
Uh-huh.
So it would be pointing down. Hang on, one more time. Yeah, down.
Downward, yep. And just casual wrist breaking again because awkward hand position. Yep, you're right. It's essentially fingers to the left, be out of the page, forces straight downward. And then obviously if the wire were to be anti-parallel, so the current was traveling against the first wire, what direction
and the forces would be opposite.
Exactly. Force would be up. And so how could we orient this upper wire so there was zero force?
The length and the length of, I believe it's the length and the magnetic field has to be in the same direction.
Exactly. So what
it can't be perpendicular, so basically
so what are our options? There's two ways we can orient it.
Into and out of the page.
Exactly. So if our wire is going the same direction or opposite to the magnetic field. Ooh, I guess we also forgot to mention, so we found the direction of the magnetic field from the first wire. What would the magnitude of our magnetic field be?
Okay, so just the first wire. So the magnetic field would be... So it would be U naught I over 2 pi r.
Exactly. Mu naught I naught over 2 pi r. That's just basic Ampere's law. That's, one of the two forms of Ampere's law you guys have to know for this class. I think, actually, yeah, I believe that's the one. That's one of two examples you need Ampere's law for this class. You have any questions about this? Honestly, it's pretty simple, so.
Yeah, this type of concept I at least got down.
Yeah.
I mean, I'll still work on the right-hand rule of different, instead of just into and out of the page, do up, down, left, right, so that way I can better see it.
Yeah. All right. So now we're going to have a long solid wire of radius A, and we're going to have it carry current, you're welcome, into the page. And we're going to have it go through the origin, so it's 0, 0. And we're going to go ahead and surround it. Let's actually go ahead and draw this. So we're going to have a wire, radius A, carrying current into the page. And we're going to go ahead and surround it by a concentric wire of inner radius B, outer radius C. So let's go ahead and fill these in. Boom. There's our two wires. Hold up. How do I do this? Can I do this? No, I don't want this one. Yeah, there we go. Alright, that's what I wanted. Didn't matter, but it's what I wanted. So we have our inner wire carrying a current, and we have an outer concentric wire carrying another current in the opposite direction. So we want to know, how do we calculate the magnetic field? Like anywhere. If R is less than A, so inside the first wire. If R is between A and B, so between the two wires. Within the outer wire. And what about completely outside?
Okay. So let's see. I1's into the page, the I2 is out of the page.
Mm-hmm. Yeah. So we have I1 is into the page. I2 is out of the page.
So, wouldn't R less than A, wouldn't that magnetic field be 0?
Why would it be 0, theoretically, if you're not incorrect? How do you calculate the magnetic field here? What law are we going to need to use?
Well, we're going to be using Ampere's law.
Exactly. What's Ampere's law?
Mu naught times... Oh, wait, before that, I want to make sure... Yeah, mu naught times I enclosed.
Is equal to what?
Yeah. Is equal to the enclosed loop of the magnetic field times DL.
Exactly.
Dot
DL. So why... So you just had an epiphany just now while you were saying that. What were you going to say?
Well, the charge is not entirely enclosed. That's what I was going to say, but then it's like, wait, that... Let's see. I think there is a reason why I believe it's 0. I'm just trying to remember what was that reason. Maybe I'm thinking about electric field instead of magnetic field. But wait, even if that's the case, that's a similar... They're both Gauss's law and... Gauss's law and Ampere's law is very similar to that.
Mm-hmm. So is our current being carried here, is it only being carried at the very edge of our wire, or is it being carried throughout the whole wire, throughout the entire cross section?
It's going through the whole section.
Yeah, so if we select a radius, let's say like right here, most of the way out, like about halfway out, so a over 2, is there zero current enclosed within that radius?
No.
No, there's a non-zero current.
Yeah, no, no, no. That's what was again. I was thinking more of Gauss's law, and I'm like, it has to be zero, and I was like, wait a minute. That's why when I said zero, I was like, something is gnawing at me saying that's wrong, and
Yes.
that's why. Because Gauss's law is the surface, and that would be zero if we were trying to do inside, but only if that was Gauss's law. This is Ampere's law, and there is a current.
And even then, for Gauss's law, it would only be the case if it were conducting, if it were
True.
conducting material. If we had
True.
if we had an insulating inner sphere or inner cylinder charge, it's not going to be zero.
Yeah, true, true, true.
So there's maybe two of these where we don't really have to do much thinking or math. What would the magnetic field be between A and B? So in this space here.
I believe you only need to worry about man, the magnetic field being produced by I1, which should be clockwise.
Well, you also have to take into consideration the magnetic field generated by I2. What's the magnetic field generated by I2 inside?
Counterclockwise, I believe.
No, I'm pulling a fast one on you. It's zero.
Yeah, yeah, it's zero.
You said you only have to worry about the magnetic field generated by I1, and I'm like,
Oh yeah.
technically I2 exists as well. It just doesn't do anything there. Yes, you're right. You only have to worry about I1 here. And what would that magnetic field be?
Into the page, so it will rotate clockwise.
Clockwise, yep. And what about the magnitude?
So for the magnitude, what do I need to worry about on that one? Because I know that I believe the magnitude's. Oh, okay. So I believe it's supposed. Oh wait, no, that should be just direction because I was going to say U naught I enclosed is over to 2 pi r. But I think if we're just worrying about the magnitude, I think it's just U naught times the I enclosed.
Wait. Why wouldn't you have to worry about over 2 pi r?
Oh wait, this is cylindrical symmetry.
Yep.
So we will have to worry about it. Sorry. Then realize that first.
So there's two ways you can approach this. You can essentially say, oh, because it's symmetry, we can treat it as if all the current is just at the origin. Or you can actually go ahead and solve the integral. Let's solve the integral here just once because it's fun.
Oh boy.
So we want some sort of what does our integration path look like again?
The magnetic field times dl.
Yeah, what is dl again?
Oh, come the heck on. How did I forget already?
It's only been 20 minutes.
I know. The length. No, wait. I know, I don't know how. I said it, and it sticks, and then just like yeeted itself.
You need to stop pressing that button on the side of your head.
I don't. It does it for me, apparently. Yeah, nope, can't remember whatsoever.
dl is the integration path for our line integral. And what does our path have to be? How do we have to integrate it? You mentioned it earlier. You said it 20 minutes ago.
just making that note for a second. Sorry. Just in case it happens. The path integral. So it's supposed to be the path of the. I believe it's supposed to be a similar path to how the magnet field goes.
Yep, exactly. So
Yeah, because it's dot, so it should be the same.
yeah, so it's going to be some sort of dotted. I mean, I'm just going to draw it here as if it's like an Amperian surface. It's a circular path around where the magnetic field is. So,
Okay.
so B dot dl. So we have our dl are these little infinitesimal vectors along each individual point along our path. And then we integrate over it to get the full length. What is the dot product of B and dl at any point along our path?
B times dl times cosine theta.
Yep, and what's cosine of theta?
In that case, since they're in the same direction at all times, cosine 0, which is 1.
Exactly. So we can go ahead and ignore the dot, and it's just B times dl. What else can we do here to simplify this? What were we able to do for electric field examples with Gauss's law at this point? We get rid of the dot product. Now what?
Well, we gotta simplify the DL. I know that. At least I believe, right? You know, I'm trying to remember all the process of Gauss's law easily, and I really need to take the time to actually go back over that.
So it's integral of E dot dA, integral of E dot dA, which we then simplify into the integral of E times dA, because we were able to get rid of the dot product. Now what do we do?
Well, I know that's supposed to equal. I know eventually that's supposed to be equal the Q, the charge enclosed over epsilon naught.
Yeah, but we're just worried about the integral itself right now.
Oh, okay. We gotta do some, move the constants out of there, out
So
of the integral.
what's constant?
E.
Exactly.
And it's also going to be B.
Exactly. That's what I was trying to get to.
Okay. I just forgot that we didn't fully get rid of the integral yet. I was like,
Yeah.
oh, whoops.
So we're able to move B out because it's a constant. So it's just B times the integral of dl. What's the integral of dl?
1 over L? Wait. No, I'm being dumb again. I know. Let's see. 1 over L squared?
No, it's just the integral of dl. It's the integral of 1 dl.
Oh, so it's just L?
Exactly. It's the total length. So it's B,
Okay.
B times the total length of our path.
All right, I was thinking about that dang on Gauss's law again, where we always had that 1 over X.
Yeah.
Okay.
So what is the total length of our path?
The circle?
Yes. So and what's the circumference of a circle?
I believe that's 2 pi r.
That's interesting. Doesn't that seem familiar?
Okay then.
That's how. I mean, that's one way where it's just B times 2 pi r. Then we just divide it over, so B is equal to mu naught I enclosed over 2 pi r. Boom! We just derived, using Ampere's law, we were able to derive at least this class's simplified version of the Biot-Savart law. So, what is our magnetic fields here for this example? Between A and B?
So it should be U naught times I enclosed over 2 pi r.
And I enclosed is what?
It's the I1?
Yep, exactly. I1 over 2 pi r. And what direction is our magnetic field in? We're asking, I asked specifically, what is the magnetic field at point R0? So essentially, along here.
Yeah, so along there, it should be pointing down.
Exactly. So I'll add a negative.
Oh, so that will make it a negative. Okay, then.
Y hat. I'm just adding a negative Y hat. Just, as a way to sort of show that we understand the direction. Or you could just...
So, I do have a question on that one. If we are doing that for like homework or anything, will that make our answer negative? Or...
If that's what it's asking for.
Okay, then. So if it's strictly saying what is the magnitude in a formula sense like that, it's just going to be U naught times I over 2 pi r. Exactly. Okay, then. And usually, that's what I was getting confused on discussion.
Yeah, and usually your homework questions are worded where it's like, what is the magnetic field, and then it'll be like enter a positive value if it's in the positive y direction and a negative value if it's in the negative y direction or whatever.
Got it. Okay then.
And like on an actual quiz, like in person, unfortunately not the case for this class, you could literally just write mu naught I over 2 pi r and just write clockwise, and you'd probably get points.
Cool. Probably, but yeah. Cool.
Probably. So, now, what's the other example where we don't really have to do too much annoying math to find the magnetic field?
Oh, is this the case that's outside the outside of I2?
Exactly.
Okay then. So it was that one.
And we'll assume the I1 is greater than I2 for positive and negative signs. So how do we get the magnetic field outside of I2?
That should be U naught times I2 minus I1.
Mm-hmm. Sure.
Oh, let's see. Over 2 pi... Well, over 2 pi r.
Mm-hmm. And is it a positive or negative y hat?
I2 is going the opposite direction, so instead of into, it would be out of the page. That would be counterclockwise, so it should be going up.
Up, sure. So positive y hat. I2 greater than I1. All right. Bada boom, bada bang. So, now we want to go ahead and find the more complicated examples. We want to find the magnetic field. We'll start inside A with R is less than A. So we need to find a way. Is there any difference with solving the actual integral on the left side of Ampere's law?
I do not think so, no.
Exactly. It's just going to still be dot product gets dropped because parallel. B comes out, integral dl is just 2 pi r. So what changes for Ampere's law here compared to these two simpler examples?
The only thing that changes should be the I enclosed.
Exactly. How do we find I enclosed for a radius r is less than A?
only other thing I see, which I don't think it would be something we need, because he didn't go over it, was J is equal to I over A.
So he hasn't gone over J yet, right? I think he goes over that tomorrow.
Yeah,
Um,
so
but
I doubt that I don't think we'll be needing that, but
do you? I mean, if you use it, it would be very helpful.
uh,
Do you know what J is?
uh, I seen it in, I believe there was supposed to in our discussion, current density.
Exactly, current density. So it's the amount of current passing through a given surface area, like a current per area, essentially passing through.
Oh, so yeah, that would definitely help us in this case.
Yeah. So how could we use it? I'm giving you the floor.
Well, I so we know the area, I believe, because all right. First of all, we make it all the way. We change it around and make it I is equal to J times A. So.
Mm-hmm. So we have
See.
I enclosed is equal to J times the area enclosed.
The area enclosed. Since it's a wire, I believe the area is supposed to be cylindrical. So. And the area of I believe I'm going to say, is this actually a cylindrical shell, or is it just cylindrical in general?
What do you mean by a cylindrical shell or cylindrical in general? I mean,
I'm trying to figure out which one's the surface area.
this here is a cross section of a wire that's running into and out of the page, like so.
Okay.
So what is the cross section here? Because the current is running, in this case, into the page through this cross section. Come on, Roger, you can do it.
That's why I'm. Yeesh, release. Okay.
What is this shape?
Oh. Cylindrical.
Specifically, this two-dimensional cross section of the cylinder.
Okay, I don't know why I'm drawing blanks. It's a. So I know it's a cylinder, but the problem is is it a shell? No. I keep down myself on this one.
What do you think? What's coming to mind?
Well, my mind keeps saying a cylindrical shell, but I'm thinking that's the I2, not I1.
Yeah. This is a solid cylinder here. This here is a solid cylinder.
Okay, so
What's the cross section of a cylinder?
to be honest, I don't remember that. Hang on. I'm actually going to look that one up because I actually really don't remember.
You're gonna facepalm. You're gonna facepalm so hard.
I probably. I think the one thing is I don't remember what really a cross section is. Like the actual.
Imagine an end cap, a cylinder's end cap.
So wait, is this literally supposed to be pi RL? Well, wait, Ned. I think I understand what you're saying. It's supposed to be like when we were doing that Gauss's law one.
If we go ahead and draw a cylinder, we have boom, we have the sides, and we have the bottom. What does this top look like?
Oh, okay. So I was thinking, okay, I was thinking way too much into it. I kept thinking of cylinder instead of the circle.
It's a circle. Thank you. I was waiting. I was trying to pull that word out of you. It's literally just a circle.
Okay, the problem was I kept thinking of the cylinder. I was not
Mm.
thinking of that. Okay.
Yeah,
That was my own thinking problem on that one. So that should be pi r squared.
exactly. Pi r squared. So how do we find J?
Yeah, that's the one thing I'm still trying to figure out.
Well, J is the total sorry. J is the current per unit area. Right? How much is is our current changing at different points when we're inside?
No.
No, it's just completely constant. So how can we find the current per unit area?
Well, it's not changing. It's always in the same one. So can you say what J is again?
It's the current per unit area.
So wait, wouldn't that be just current times area?
Or divided. We literally just take the total.
Oh, per. So divided. Sorry.
Exactly.
Yeah.
We literally just have to take the total current running through, so the total current being I1, and divide it by the total area of the wire. That's it.
Oh.
What's the total?
Okay.
What's the total area of our wire's cross section?
I'm pi r squared. Yeah, pi r squared.
Yeah. What's the radius of our wire here?
Less than a.
Well, it is A. A is the radius of our wire here.
Okay,
Yeah, because this R here is for a arbitrary R anywhere from 0 to A.
okay then.
So then from this, we can just get I enclosed is equal to I1 pi r squared over pi a squared. So r squared over a squared. Boom. That's it.
Okay then. Yeah, okay.
And now we just plug it into Ampere's law. And what do we get for the magnetic field?
U naught times I see that'd be r squared over a squared. And then that's over 2 pi r, and then I'm pretty sure there's going to be simplifications on that one. So I should be U naught I1 r over 2 pi a squared.
Yep.
Okay.
And what direction is it in? Along this x-axis here?
Oh, should be should be still going down, I believe.
Exactly. So we'll throw a negative y hat. Boom. Magical. Amazing. That wasn't too bad, was it?
Once I figured out what that meant.
Once you figured out what a cross section meant.
Yes. Okay.
You're totally golden.
Yep.
So that was the simpler of the two.
Oh God.
Now we're gonna get into the fun of this outer wire. So we're gonna have to find our enclosed charge when we're somewhere in the outer wire. For example, right here.
All right. But we have to include I1 into this as well.
Yes, we do. So let's go ahead. Let's include that. So I enclosed is going to equal. We know it's going to be all of I1, and then we'll throw a negative sign because we know that any contribution from I2 is going to be opposed to I1.
Yeah, and so it's going to be some part of I2.
Mm-hmm.
So So is this the case that we need to use a cylindrical shell for the area 1 this time?
Yes.
Okay, then. Alright, so I enclose minus the I enclose of 2. So that would still be minus J area enclose of 2.
Minus J, yep. And so what would that enclosed area be?
Where did that piece of paper fly off to now? 2 pi RL.
2
Should
pi,
be, right?
That would be the surface area.
Oh, cylindrical shell, please.
That would be the surface area of this part of the cylinder. Well,
yeah,
we're still worried about the cross section. So essentially, what we want to know is what is the area of a donut?
a circle, but minus that part of minus the middle, basically.
Exactly. It's the circle minus the hole. So and what's the area of the hole?
Also, 2 pi r. Okay. The area of the hole is pi r squared.
Exactly. It's just the smaller circle. So the area of, if this was A and this was B, this area would be pi B squared minus pi A squared. So pi, oh god, what have I done? Okay. So just be pi B squared minus A squared. Oh, what the hell am I doing? There we go.
That means that'd be the same. Just pi. So that should be J times pi B squared minus A squared.
Or in this case, the outer radius, the B squared, would be R squared, our radius, our general radius R out.
Okay.
And what would our inner radius be?
A?
No, it would just...
Oh.
It'd be our radius...
The radius would... Oh, so the radius would be B this time.
Yes.
Because... Okay.
I poorly chose my two radiuses for my donut example. So yeah, so pi R squared minus B squared. This is J2. So how do we get J2?
Well, okay, so the current, it's the total current. So we will still need I2, but I believe we may need I1 as well.
To calculate J2?
I believe so.
Why would the current inside this inner wire matter for finding the current density of the outer wire?
Oh.
It don't.
Yeah, it don't. So it's just I2.
So we have I2 divided by the total area of the outer wire shell.
So this time, this is where the cylinder... So the total... Oh, wait, no, this is still the cross-section, isn't it? So 2 pi r squared.
Not 2...
Oh, wait. So, yeah, pi r squared, sorry.
Yep. But it's not the full circle. We also it's this whole big circle minus this inner circle here.
So we still have to... Okay, so it's still... It's still pi times r squared minus b squared.
Yep, and in this case, r, the outer radius, would be the total outer radius all the way out, which would be c.
So c squared minus b squared. Okay, then.
C squared minus b squared. So then we can plug it all in. I enclosed. is equal to I1 minus I2 r squared minus b squared over c squared minus b squared. I'm sure maybe there's some way to simplify it further, but probably not, and I don't want to do algebra for 20 minutes to figure it out.
Okay.
So now we just plug it into Ampere's law, right?
Oh, God. Oh, that's going to be a mess to try to simplify, so I guess just plug it all in.
Yeah, I'd say I'm just going to do...
You not times all that I enclosed.
I'm just going to do this mu naught over 2 pi r times all this ugly mess. I1 minus I2 r squared minus b squared over c squared minus b squared. And we'll throw a negative sign, negative y hat direction. Because we've defined I1 as the positive one, which would be downward. Boom! Magic.
Oh, so that's okay.
Yeah, that's it. I mean, unless you want to spend 20, 30 minutes simplifying this.
I was just trying to figure out the direction part. I was like, all right,
Yeah.
I2 is out of the page, so... And then you said that, and I was like, oh.
Well, all it depends on, if we were to write it as I2 times r squared minus b squared over c squared minus b squared minus I1, then it'd be positive. All it depends is what direction we've defined.
Okay.
So, like, for this one, you said you wanted it to be I2 minus I1, and I was like, okay. And then, so that would mean you'd want the positive sign here. If we were to define it as I1 minus I2, you'd have to throw the negative sign out front.
Okay. So it just depends on how we write it. Okay, then.
Exactly. All depends on how we write it. And if we define I1 to be positive within our bracket, then we have to throw the negative sign out front because it's in the negative y direction.
Okie dokie.
So, honestly, it's pretty simple. It's essentially just right-hand rule Gauss's law. It's really not much to it, and it just takes practice. And thankfully, I think you guys have another class where you're going to work more with Ampere's law.
On Ampere's law, yeah. And, yeah, because I really don't... just went over the class notes. We didn't even go over J is equal to I over A, so that pretty much should be the next part of the class.
But even though you technically didn't go over it, it's so simple to understand. It's literally just... For this class, you're going to only see uniform current distributions, so it's always going to be total current over total area.
Got it.
And then you just, I think you go over, I think tomorrow you go over Ampere's law and motional EMF, and then the last class on Friday, I think you finish up with motional EMF, and then you just go over, I think inductors on Monday, and then you review Wednesday, and then the class is over on Friday.
Yeah, because we got Faraday's law, introduction to RL circuits, and then LC and RLC circuits left as well.
I don't believe he actually covers RLC circuits. I think you might skip over that.
Okay. Well, it is on Flip It.
Yes, but he has skipped that part of the class the last 2 semesters because honestly, it's not really worth your time. It's just another thing to sort of throw in to confuse you and get people worried studying over. And it's so much easier to reapproach it after you have a baseline in differential equations.
Oh, you gotta deal with that.
Yeah.
Fun.
Like I went over it when we go over RLC examples in Physics 224, and then also in Electronics Lab. So, but they're not too bad as long as you understand differential equations. And because this is the 100 level class, and 99.9% of the students in here haven't taken DiffyQ, there's no point.
Differential equations. That's like Calc 3, right?
No. It's a separate class. It's differential equations itself. I think it's like Math 225 or something.
That one.
Yeah.
Yeah, I just took it. I just literally finished that the other day, like last semester.
Who did you have?
Uh, wasn't that great a teacher if I can't remember it.
Was it the old
It was,
guy?
huh?
Was it the old guy?
It wasn't oh god, yes. Yeah, I mean,
With the
he did okay. Let me at least say that he was good. It was just more self-learning, and that when it came to that, I was like, ugh.
Mhm.
Yeah,
Is
that
it,
was the only thing. Like, I got the concept. It was just more since the self-learning, and that just made it trickier.
is it Patra? Florian Patra?
Uh, no.
Oh, okay. I was gonna say because I had him, and I'm pretty sure he showed up drunk for all the lectures, and he'd disappear every class in the middle for about 5 minutes to go smoke.
Wow. Yeah. No. Wasn't like that.
It was wonderful. I miss in person classes. All right, that's pretty much it for today. Hope this helped out. Good luck studying for tomorrow. With the good old Ampere's law and the BS law. Honestly, it's going to be really simple. You're just going to see like infinite wires and have to calculate the current based on them. And
Yeah.
you might see a wire loop, which for fun, how do you calculate the magnetic field due to a loop of wires? If you have an infinite
Oh, that.
if you have like an infinite loop going along, how would you calculate the magnetic field for that?
Where's that note? uh, Magnetic field from loop. So U naught times I over 2R.
Not.
Well, that's a loop.
That's for a loop, but even then, that's not quite it.
Okay,
I'll
so
give you a hint. It's on your formula sheet. It's the one equation from Unit 18 and 19 we didn't look at today.
so oh wait, the one and you're asking for the magnetic field.
Yes.
Okay, so it's 1/2 U naught uh NL. I mean NI.
Yep. Half mu naught Ni, where little n is the number of it's the turns per unit length. So you might see a question on your quiz where it's like an infinite, magnetic coil with 20 turns per unit length, or 20 turns per meter. Blah blah blah. What's the magnetic field inside and outside it?
So inside and out.
Yeah, and one of them is 0. Fun fact.
Uh I'm guessing the inside is 0, right? No.
I'm not actually sure. I can't remember which one.
Yeah, one of them. I'm trying to look at this. I'm just trying to look at something like this that someone else seeing which one's 0. But oh god.
Yeah, don't worry about it too much. Just Google it. Refresh yourself, and the quiz tomorrow won't be too bad. Once you get into motional EMF and Faraday's law and Lenz's law, it gets a bit more complicated. But even then, it's not. Even then, it's not too bad. All right, I'm out of here. I gotta go prep for 121. Thanks for popping in. Good luck studying.
Okay, thank you.